Thermodynamic geoengineering converts the heat of global warming to productive energy. It is an antidote to the hothouse Earth scenario, in which system feedbacks and their mutual interaction could drive the Earth system climate to a point of no return, whereby further warming could become self-sustaining. The incoming solar radiation and outgoing thermal radiation at the top of the atmosphere are in equilibrium, but for the 0.6 watts per square meter residual surface heat flux indicated by the green arrow. The residual heat is shown being injected beneath the surface, and in fact 93% of the heat of warming is going into the oceans. At the surface, the absorbed solar radiation plus the back radiation resulting from greenhouse gases are offset by the radiation from the surface minus sensible heat, latent heat of evaporation, and the residual heat. Evaporation offsets about 25% of the greenhouse effect that makes the surface 30 degrees warmer than it otherwise would be. Evaporation dries the surface but increases the water holding capacity of the air by about 7% for every degree of warming. The increased water holding is producing atmospheric rivers and arguably higher storm surge levels and more rainfall from tropical cyclones that are more intense and larger. The increasing sensible heat of the oceans is also producing thermal expansion and sea level rise. Latent heat is a two-way street. Surface heat can be relocated just as easily to below the surface by a heat pipe that converts a working fluid like ammonia to a vapor and then condenses the vapor at depth. If that vapor passes through a heat engine, a portion of the heat is converted to useful work, which is the object of burning fossil fuels in the first place. Since the surface area of the Earth is 510 million square kilometers, at 0.6 watts per square meter, a doubling the residual heat produces about twice as much energy as fossil fuels. Although the heat of warming is measured in watts per square meter, it doesn't accumulate uniformly. It accumulates in the tropics and is distributed around the globe slowly by the thermohaline circulation and more rapidly by the winds. The heat moves from the tropics towards the poles. It accumulates and is mixed in the top 100 meters of the ocean, but thickens from east to west in the Atlantic and Pacific and in the opposite direction in the Indian Ocean. The thermohaline circulation transpires in a small segment of the entire ocean. Heat pipes can draw off heat that would otherwise migrate towards the poles where it melts the ice caps, producing sea level rise and other detrimental environmental outcomes, moving it instead into deep water. In the process, a portion of the heat can be converted to useful work, and this transformation takes place largely in the more tranquil portion of the ocean where the thermohaline is not impacted. In this overview of the tropical segment 20 degrees either side of the equator, the heat pipes are shown in orange, the heat engines are yellow, the pipes returning condensed working fluid back to the surface are purple, evaporators are violet, the continents are brown, and the thermocline circulation is red. In the Pacific, circumpolar deep water in blue originates in Antarctica, circulates through the ocean, and returns. As the following NASA video shows, the thermohaline is operating mostly below 1,000 meters, rising to the surface only in the west once the water has been warmed. In the Atlantic, Arctic bottom water in mauve rises and loops below 1,000 meters above the equator and joins with North Atlantic deep water descending back towards Antarctica. The thermohaline circulation is driven by global density gradients created by surface heat and freshwater fluxes. The Gulf Stream carries heat north from the tropics and southern hemisphere until it is lost in the northern Atlantic, Nordic, and Labrador seas. One of the principal aims of thermodynamic geoengineering is short-circuiting this movement of heat towards the poles without impacting the thermohaline circulation. In this animated GIF, the heat of global warming is represented by burning light bulbs in yellow. Each of the 14 light bulbs represent the 338 terawatts of heat that is accumulating annually in the world's oceans. Heat pipes move this heat very rapidly, less than a minute, to the deep water where it is converted in part to work, but most is sequestered temporarily. The part converted to work becomes a black spent light bulb and ultimately migrates back into space. It takes 250 years for the heat moved to deep water to return to the surface at a diffusion rate of 4 meters a year. This migration is represented by 10 incremental movements of 25 years. Back on the surface, in 250 years, another light bulb is burnt out and moved to the deep as another tranche of heat is converted and sequestered. This recycling of the heat of global warming and conversion to work continues for about 3,250 years. Since the incoming radiation reaching the tropical ocean surface is about 161 watts per square meter, it takes considerable surface area to produce 250 megawatts of power. This energy island is an equilateral triangle of 735 meters aside. It consists of 55 segments 73.5 meters aside that cover a surface area of about 235,000 square meters that produce 200 megawatts of OTEC power and another 50 megawatts of solar, wind, and wave energy. On its underside, wave intensifiers produce hydraulic energy that is collected in the yellow pipes on the upper side of the island and directs pressurized fluid into the yellow conversion plant at the back of the island that converts the fluid in a generator into electrical energy. The solar power and wind electricity is collected in the green transformer that sends power to either the thrusters on the underside of the plant that power and steer the island or to the electrolyzers far below. Hydrogen from electrolyzers is transferred back to the surface where it is collected in the red tanks or to the red fuel cell at the back of the island when solar, wind, and wave energy isn't available to operate the system. The 22 heat exchangers at the back and bottom of the island collect the warm surface water used to boil the working fluid and produce vapor. In front of the heat exchangers is a screen that deflects aquatic life and refuse away from the heat exchangers. The vapor flows down the heat pipe to a depth of 1,000 meters where it is transferred to a turbine that produces electrical energy. Electrical energy is sent to the electrolyzers that produce hydrogen and oxygen, and with the negative emission CO2 OTEC process, a carbonate or bicarbonate that sequesters CO2 and mitigates ocean acidity. The net effect of the process is to decrease evaporation, surface heating, storm surge, and rainfall from tropical cyclones that are less intense and smaller, and for each gigawatt of continuous power generated, 1.1 million tons of CO2 emissions are avoided while consuming and storing 5 million tons of CO2 a year. The spent vapor is sent to the deep water condensers that turn the vapor into a liquid that is pumped back to the surface.